Gravitational waves are waves through the fabric of space. It's one of the types of wave phenomenon that exists in nature. There are all kinds of waves in nature. Electromagnetic waves, which are light and X-rays and radio waves. There's sound, which is a compression wave that travels through materials. There's all kinds of vibrational waves in solid materials. And then there's gravitational waves, waves through space itself. They were hypothesized about over 100 years ago, but the first detections of them only came about 2 years ago. They're extraordinarily difficult to detect, even though there's waves traveling through space that have loads of energy in them. And it's a bit of a surprise that all the waves that have been detected so far apparently come from the merging of binary black holes. There's two black holes orbiting each other. They come together and then merge into a single black hole. So all the 3, maybe 4 groups that have been detected come from this kind of event. It wasn't expected that anybody would see the merger of binary black holes because they didn't think there were enough of them in close enough proximity to believe it. But that's what they come from. Let me first talk about gravity. There's basically 2 theories of gravity that people use to make computations about gravitational momentum. There's Newton's law of gravity. This is Isaac Newton. He published this. He came up with this idea in the late 1600s. He conceptualized gravity as an attractive force between all things that have mass. So we usually see it in this form. So this shows the magnitude of the gravitational attractive force between objects 1 and 2. And down to. And this is a very successful theory of gravity in that it very accurately predicts the force of gravity for many situations. For example, the Jet Propulsion Laboratory navigates probes around the solar system. And in order to do this, they have to be able to accurately calculate the gravitational influence as a probe passes a planet with its moons and everything. And they're able to do that because it makes accurate predictions of the force of gravity. But it's not completely accurate. And there are some things in nature that it simply doesn't describe at all. The modern theory of gravity is called general relativity, and it was published by Albert Einstein in 1916. It's a very different concept of gravity. In general relativity, time is treated as a dimension similar to the 3 spatial dimensions. And the presence of matter and energy in this 4-dimensional space-time causes curvature in the fabric of space-time. And we are, in a sense, moving through time, so we're moving along curved paths in space-time. So that we see this because as it moves through this path in space-time, it curves and accelerates in one of the spatial dimensions, one or more of the spatial dimensions. Very different notion of gravity, but even more successful in Newton's law. It agrees with Newton's law where Newton's law gets it right, but where Newton's law is inaccurate, like in the case of really strong gravitational fields, it remains accurate. And it also describes some things that Newton's law doesn't even touch, like the existence of black holes. It's not really consistent with Newton's law of gravity. Black holes are objects that are so compressed that nothing can escape their gravity, not even light. They also describe gravitational waves, what I'm going to talk about today, which is inconsistent with Newton's law. A thing called gravitational lensing, the effect that gravity has on light. That's correctly described by general relativity. And of course, the whole cosmology theory is a direct manifestation of Einsteinian gravity. So this is sort of the modern theory of gravity, and it's a very successful theory. Shortly after Einstein released his modern theory of gravity, another physicist named Schwarzschild was studying it and derived a specific case of
Einsteinian gravity, the gravitational field generated by a spherically symmetric object. That's a useful form of a gravity theory to use because most objects that generate gravity fields are roughly spherically symmetric, like the Earth, the Sun, other stars. And it also was the first theoretical indication for the existence of black holes. It directly came out of the theory. Black holes their existence wasn't verified until maybe the 1980s, but this was the first theoretical indication that they might exist. Another mathematician, physicist named Henri Poincaré, realized that relativity implies that waves should travel through space, that when an object moves, it emits a ripple that propagates out through space-time that carries off energy. So literally, when I move my hand, it makes a tiny ripple propagate through space. Now, the amount of energy that my hand moving releases in gravitational waves is vanishingly small. It can never affect anything. But in the case of heavier things, like two heavy objects orbiting each other in space, it can actually carry significant quantities of energy. So here, this is supposed to be two things like heavy black holes orbiting each other close, and they're sending out waves in space. Now, this shows waves propagating in a two-dimensional surface. Space is not two-dimensional, it's three-dimensional, but it's more complicated to show how it propagates in 3 dimensions. But you get the idea. It's waves are spun out, or radiated out through space when objects move. And the fact that this happens was verified in the 1970s with the discovery of a binary system called the Halsey-Taylor binary. It's 2 neutron stars. A neutron star is one of the possible remnants from the explosion of a heavy star at the end of its life. The other possible remnant is a black hole. But a neutron star is more observable. For example, it has a magnetic field, and interaction with material around it with this magnetic field causes beams of radiation along the magnetic axes. They also rotate, and so they sweep around in space, and if the beam happens to sweep past the line of sight toward us, then a pulse is released that we will see, and then the object is called a pulsar. So, and one of these things is a pulsar. A pulse is about 17 times per second, and it's in an elliptical orbit, moving around its binary partner. The binary partner is not shown here. So this thing's moving around. When it's moving toward the Earth, every successive pulse is released when it's a bit closer to the Earth. So we see a higher frequency. And when it's moving away from the Earth, we see a lower frequency. So there's a periodically changing frequency of this pulsar. And this is what you see. So this is the pulse rate graphed as a function of time. And here you see 12 a.m., 12 p.m., 12 a.m. The orbital period, the amount of time it takes for this thing to orbit once, is about 7 3/4 hours. And you can see how the pulse rate goes up and down. It doesn't vary a lot. 16.945 down to 16.915 pulses per second. But the pulse rate of pulsars is, for most of them, it's extremely regular. In other words, very reliably stays the same value. And that makes it possible to measure the orbital period, the amount of time for one complete cycle, very precisely to within like a microsecond. That's useful for studying gravitational waves because if these things are emitting gravitational waves as they orbit each other, then the waves are carrying off energy, which comes from the orbital energy, so they should be spiraling toward each other, which means that the orbital period should be changing over time. And since it's possible to measure the orbital period so precisely, it's possible to measure that change. And that, in fact, is the case. Here's the orbital period through time. Here's 1975 when it was discovered. It's 2015. It's not changing very fast. You can see in the first 5 years it went from 7.7519395 hours to 7.7519394 hours. That translates to only about 76 microseconds per year. That means the orbital period is getting shorter by 76 microseconds every year. But that's quite a measurable change, even though it's not a big change. And general relativity can predict what the magnitude of the change should be, given the masses of these two things and everything. And here's the prediction, 76.67 microseconds per year, and the observed is almost exactly the same. So this is taken as strong evidence that not only do gravitational waves exist, but the general relativity correctly describes them. So this is the first indication that gravitational waves actually do exist. 76 microseconds per year doesn't seem like much, but that actually translates to the emission of a lot of energy. About 7.35 trillion watts. In other words, this is the rate at which energy is being drawn off of orbital energy and radiated out into space as gravitational wave energy. That is a truly stellar level. That's about 1.9% the sun's luminosity. And the sun doesn't emit gravitational waves, it emits electromagnetic waves, light waves. But so I'm kind of comparing apples to oranges here. But the point is that it's emitting energy at a truly stellar rate. Compare that to the gravitational wave luminosity of the solar system. You know, all the planets are orbiting the sun, including the Earth. And so they are emitting gravitational waves. But if you calculate the wave emission from all the planets, put it together, it's 6,200 watts. That's like 4 microwave ovens. So that's utterly negligible in terms of affecting the orbit over time. Even a big object, if you replaced the sun, if you replaced the Earth with an object the size of the sun and had it orbiting at that distance, it would still be only emitting energy at about 44 trillion watts. And that's, 150 billion times lower than this system is still negligible compared to stellar rates of energy emission. And this rate of energy emission actually is substantially reducing the orbit of that thing. That graph that I had showing the orbital period decreasing, if you extend that out in time some, like 150 million years, the orbital period will go all the way to 0. And this object will merge together. So this is 2 neutron stars. They will merge together, probably form a black hole. And when it does that, you can see the closer it gets to the merger, the faster the orbital period drops down. That's because it'll be emitting gravitational waves at a greater and greater rate. And when it merges, it'll be emitting gravitational wave energy at a rate that's millions of billions of times what it is now. And that burst would actually be detectable by the detectors that are in place now. Of course, those detectors won't be around in 140 million years, but unfortunately the universe is so large that there's trillions of objects like this, these heavy objects in close binary systems. And there are different stages of their in-spiral, so you can expect to see some even over a short time scale like a human lifetime. So what we've been seeing is the mergers of these. This is what a black hole binary would look like if you were close to it. This is a simulation. This is not the real thing. So it's distorting the view of the sky around in back of it. Okay, so how do you detect gravitational waves? Well, in principle, it's quite simple. Here's a laser beam, shines on a beam splitter, like a half-silvered mirror. Part of the beam goes that way, part this way. They reflect off mirrors at the end. They come back. Part of this beam goes this way, part of this beam goes through. This is called a Michelson interferometer. And they show the beams rejoining, and they're shown rejoining in phase. That means the peak of one matches the peak of another. In that case, the light detector here sees a bright light source. But if one of these legs changes in length by even a tiny bit, then these waves won't be in phase. If they're like half a cycle out of phase, then you won't see any light here. So if one of these lengths changes even a tiny bit, it changes the brightness of the light seen here. It's a way of detecting the change in the length of one of these, even if it's a really slight change. And that is useful for detecting gravitational waves because theoretically, when a gravitational wave goes through space, what it does is it shortens the length of space as it travels through. It shortens the length of space in a direction perpendicular to its direction of travel. And now, even these large waves coming from the merger of binary black holes, the amplitude of these gravitational waves is extremely small, and the change is expected to be a tiny fraction of the diameter of a proton, which is millions of times smaller than an atom. And I really don't know how they do this, but I mean, the experts say that they're doing it right, and they can actually detect these extremely small changes when a gravitational wave comes through space. And I'll show you where these things are. This is the northwest U.S., and if I zoom in, there's Washington State. Zoom in. There's one of them. It's the two legs of that thing. They're 4 kilometers long. This is near Hanford, Washington. They put it in a relatively remote place because they're trying to detect an extremely small motion, and even very slight, like seismic activity. A car running through a pothole nearby can cause noise in their detector, so they have to be relatively remote. And the other one, there's 2 of them. This one's near Livingston, Louisiana. You can actually tour this thing. Once a month they have an open house. It costs like $10 or something, but you can see how it all works. And so I'll explain in a bit why you need more than one, why a single detector isn't sufficient. Now, this graph shows the sensitivity of the various detectors or conceptualized detectors or experiments that people want to use to detect gravitational waves. The horizontal axis is frequency, so you can talk about frequency of gravitational waves. Same as you can talk about frequency of sound waves. You know, the middle C on the piano keyboard is a frequency of 262 hertz. That's 262 sound waves per second. The frequency of electromagnetic waves is, you know, when you tune into 96.7 FM, you're tuning into 96.7 megahertz, 96.7 million cycles per second. So you can talk about gravitational wave frequency too. And the colored regions on here are the expected frequencies from various types of known objects in the universe, like, for example, compact binary inspirals, like these binary black holes that are merging together. This is the expected spectrum, this color. In fact, the red is one of the actual detections. So it's similar, but it was a fairly high amplitude one, so it sticks up above it. This black line is the sensitivity limit of these instruments. LIGO is the name of this instrument. Anything above it is detectable. So this dips down into here. A LIGO is advanced LIGO. That's what's running now. It was upgraded several years ago. So here's dips down a little lower into this region and this region. So it should be, in principle, it should be able to detect core collapse supernovae. That's another type of event that occurs that will produce gravitational waves, although they have not yet detected any of those. Okay, so let me talk a bit about this. This is LISA. This is the European Space Association has proposed building one of these interferometer things in space with a much longer length of arm. But if it ever gets built, it won't be operational for several decades. But it'll be able to detect some of these other kinds of sources that are thought to exist to emit gravitational waves. And it's kind of interesting where this thing will be. This is the sun, the blue thing's the Earth, and the other 3 things are the satellites that'll make up this sort of equilateral triangle configuration. It's exaggerated in size here. It'll only be 1 million kilometers on the side, but here it's probably showing me 50 million. But anyway, hopefully this will get built someday, but not for a long time. Okay, so this is the type of gravitational wave expected from one of these binary mergers. So the things are spiraling in, and then in the last fraction of a second, as they spiral toward each other, the amplitude of the wave they produce gets bigger, and the frequency gets up, and they merge together, and then the signal goes away. So this is the type of signal you'd expect to see. Now I'll show you an actual detection. So this doesn't look exactly like the other thing, right? It's a much more jiggly signal. Keep in mind that all the jiggle in here is thermal noise in these detectors. They're trying to detect an extremely small motion of the length of one of these detector arms. So The reason it doesn't look like a smooth curve like that is because just seismic noise, thermal noise, that has nothing to do with gravitational waves. But notice that there are two curves here, the peach and the blue curves. Those are the signals from the two detectors. They're thousands of miles apart, but they got the same signal within milliseconds of each other, and there's really nothing else this could be except a gravitational wave, because nothing else could cause the same signal at the two detectors within milliseconds of each other. Gravitational waves travel at the speed of light, according to the theory, and so they should be detected within. So this is why you need more than one detector, because this way you can be sure that that's what you're getting, this gravitational wave. This is another one of the detections. This was the most recent one, made in January of this year. And the black line is the best fit model. So they do a computer simulation to try and model what exactly happened. What were the size of the objects that merged together? How far away are they? What's the orientation of their orbit with respect to our line of sight and all that stuff? In other words, they vary those parameters until they get a curve that most looks like the signal that they got. That way they can get a theoretical idea of what was the system that emitted this. This is the leftover noise. So this is just thermal noise in the detector that has nothing to do with gravitational waves. And here's the 4 events that have been detected. These 3, the ones that begin with GW, there's high confidence that they were actually gravitational wave events. The other one is not as high. So 3, maybe 4 of these detections have been made so far in the last 2 years. Here's some parameters of the best fit model. So here's the first event, was the strongest. And according to their model, this was a 36 solar mass black hole combining with a 30 solar mass black hole. So M sub circle with a dot in it means the mass of the sun. It's about 2 octillion tons. So this is 36 times the mass of the sun, a fairly hefty black hole. So these are 2 pretty large black holes merging together. And here's the combined mass once they merge together. Now there's plus or minus just because there's uncertainty when they try to fit the model. But it's roughly this much. You may notice that the total mass is less than the sum of these, because one of the other implications of relativity is that when an object has energy in it, it's heavier. So when you heat up water, you literally make it a tiny bit heavier. So when it gives off energy, it gets lighter. So when these things emitted gravitational wave energy, when they merged, they gave off quite a bit of energy, and that made them lighter. And it corresponds to about 3 times the mass of the sun in mass. That's a lot of energy. That's thousands of times the amount of energy emitted in a supernova, which is the explosion of a star. And those are extremely energetic. So these are just the best fit parameters from the 4 things. Whoops. Here I just thought I'd draw the size of the hole in space. A black hole is essentially a hole in space. And here are the size of the event horizon, as they call it, for these 8 black holes, and then the combined merger one, compared to the eastern U.S. And you can see, they look pretty large, right? But keep in mind, this is 62 times the mass of the sun. So it's actually a pretty compact region. So this is a lot of black hole binary mergers. I didn't expect to see any black hole binary mergers, simply because in order for them to in-spiral over the time scale of the universe, they have to start out pretty close to each other. If they're further apart, then the rate at which the wave emission bleeds energy off is so slow that they won't in-spiral in a time scale like the present age of the universe. They have to be relatively close. People didn't think there were enough of these black hole binaries in a close enough proximity. So somehow, these black holes are entering into these black hole binary systems. And how are they doing that? That's it's a bit of a more conventional question, because it has to do with how black holes are formed from stellar explosions and so forth. It's complicated by the fact that it's very difficult to tell where these explosions are located. I mean, where these black hole binaries are located. This is a map of the entire sky projected onto a surface. So this is the entire sky around us. The red color is probability of where this the first event came from in terms of direction in space. So it's kind of a fuzzy swath. We don't know exactly where it came from in space. And look at the distance to it. Somewhere between 700 million light years away to 1.6 billion light years away. That's a huge. I mean, in other words, the wave came from somewhere in that huge range. There's millions of galaxies in that region of space that is the likely origin of the source of that wave. So my point is, not only do they not know like what part of a galaxy this thing occurred in, but they don't know what part of the cluster of galaxies. If you could say, okay, the wave came from the center of that star cluster, that would give you some idea of how that thing came into being. But you have basically no idea where these things are. But people that study star formation and how stars go through their lives have some things to say about how these black hole binaries might have formed. When stars form, they form in big groups, hundreds of stars, and they form a wide range of masses of stars. There's lightweight stars and heavy stars. The heavy stars go through their lives fastest, and they blow up early in the history of the star formation event. So this is a young cluster of stars that's formed all together. The blue things are supposed to be stars, lighter weight stars that have not yet finished their lives, and the orange things are black holes that have formed from the explosion of the heavy ones. So you get a bunch of heavy black holes and lighter weight stars. Now these things are all orbiting the center of mass of this star cluster, and they can have a lot of close interactions with each other, two objects coming relatively near each other. And actually I do want to do this demo, even though they can't see me out there. When a light object and a heavy object interact, the light object winds up getting the biggest boost. And here's a light object, here's a heavier object. So this thing had its velocity changed a little bit, but not nearly as much as that. And the same principle is true for these, stars that are interacting with each other. They don't bump into each other, they swing past each other, but the light object runs off with more energy than the heavy object. And what that does in a star cluster, it causes the lighter weight objects to move toward the outskirts of the star cluster while the heavy things sink toward the center. And I just got some freeze frames. They're all orbiting, so they're moving in space. So this is like a freeze frame of a later moment in time. And let me just go through a bunch of iterations of this. So the heavy ones are concentrating toward the center, right? So they wind up in a tight group. People have simulated this and have noticed that in their simulations, the heavier things wind up concentrated at the center. Now they're in close proximity to each other where they can join into binary systems and form these close binary systems. So they're just trying to explain where these close binary systems of black holes could come from. And I was looking at a paper that simulates this. First of all, this is a histogram showing the masses of the black holes that were involved in the 4 gravitational wave events that have been seen. So what does this mean? One black hole between 0 and about 7.5 solar masses. 2 black holes between 7.5 and 16 solar masses, and so forth. So I'm just showing the distribution of masses of these things. I put it in that form because they express the results of the simulation in terms of that. This is a kind of a complicated graph, but in one run of their simulation, the black holes that wound up in the center of this cluster were relatively lightweight. This is the red thing right here, so nothing heavier than like 16 solar masses. in a different run, they got some heavier ones, and then in a different run, the purple, they got even heavier ones. And let me just isolate that one, because that one looks most like the distribution of black holes that have been observed. The difference between these different runs is the composition of the material from which the star is formed. So when the universe formed, the only elements that existed were hydrogen and helium. And all the other elements are generated by stars and nuclear processes associated with stars. As time goes on, the composition of the material from which stars form is enriched in these other elements. In the solar system is a relative latecomer in the universe. The material in the solar system is about 1.4%, all the other elements other than hydrogen and helium. It's still mostly hydrogen and helium, but it has like 1.4% of all the other elements. That corresponds to a Z of 0.014. In other words, Z is the fraction of stuff that's all the other elements. So the red is stars forming from a material that's richer in the other elements than the solar system. But this is the most primitive material. In other words, nearly pure hydrogen and helium. 1/14 the amount that's of the other elements that are in the solar system. So just from this, one might infer that these black holes were formed in various star clusters early in the history of the universe, and because the simulation that they're most like is black holes formed early in the history of the universe. So these appear to. This is speculation. I mean, it's circumstantial evidence, but that's consistent with these simulations. And that's interesting because there's a lot about star formation in the early universe that we don't know because it happened long ago. It's not happening now. And so this may give us information about the star formation in the very early universe. So LIGO is going to undergo another upgrade, which will lower its sensitivity limit down even further and dip into these other regions. What they really want to detect is core collapse supernovae. When these high-mass stars end their lives, they explode, and there's a lot that's not known about how that explosion occurs. These gravitational wave pulses that come from them come from the very inside, the core of what is doing the exploding. That's the part that they don't understand. So they want to see. So this can serve as a diagnostic of what's going on during that explosion. One of the other experiments that people want to do is just to detect the really low frequency gravitational waves, because part of that is thought to come from the extremely early universe and could tell us very fundamental things about the nature of physics in this universe. So this is a new window onto the universe that we never had before and could tell us quite a variety of different things. So anyway, didn't take as long as I thought. So if anybody has questions, I'd be happy to try and answer. You mean that animated thing? It's not the way the waves actually look. This is kind of an analogy. This is showing waves in a two-dimensional surface. Actually, the real waves are going on in 3 dimensions. Is that what you mean? Okay. Yeah, because it's actually possible to show how it causes space to change its shape in 3 dimensions, but it would be graphically very complicated. But this gives you an idea of what's meant by waves being propagated out through space. Anybody out there in the internet line? Oh yeah, it's definitely shorter than I thought. You got rushed. Yeah, maybe not population 3 because, well, a Z of 0.001 is not population 3. That's population 3 is like 0, Z of 0. What he's talking about is the very first generation of stars that formed from just hydrogen and helium were quite different from stars that formed afterward. And because the presence of the other elements has a big effect on the formation process. But these, yeah, I mean, that simulation is a Z of 0.001, which is, definitely not. But that's still pretty early. But I just wanted to talk a little bit about, where these things might have formed. So the fact that looks more or less like that, I mean, that's not real strong evidence that this is where they actually come from, but it's consistent. In other words, we know the waves are coming from these black hole binary mergers. Maybe this is how they formed, maybe not. Yeah, I know. Right. And in fact, I think it's we know about black holes that are much larger than that, like centers of galaxies, but I don't know that many stellar mass black holes have ever been detected, right? Maybe a few. Black holes are very, very hard to find because they're black holes and they don't emit any energy. Oh, really? Oh, yeah, that's right, in the binary systems. Yeah, that's true. Yeah, but this is, maybe it's this mid-mass range or this heavier stellar mass black hole. I can't remember what it is, but these are in a range that are kind of new. But I first read about this in the 1970s when I was in high school, about detecting gravitational waves in this way, and they detected 2 years ago. I mean, I thought they would never detect anything. But it's so hard to detect these things. Mm-hmm.
Well, actually, my question is about what kind of techniques are they using to minimize the noise? Or I'm trying to figure out that other like periodic things, that they can identify if they can find out.
I don't know much about the technical stuff of how they do it. I don't know how they detect these extremely low amplitudes because they're so small compared to the noise. I don't know. How do you detect the length change of a 4-kilometer thing that's a million times smaller than an atom? I meant to sort of study that and see some of the principles involved in how they do that, but I really don't know anything about how it works. But that's why it took 30 years after building the instrument for it to work, because they're trying to detect something so subtle. Well, anywhere on Earth? Anywhere on Earth. Well, yeah. Well, it's probably true of this as well. Yeah, that's why Lisa, the one in space, will be Thanks for coming. That's it. That's all I got.